At a conference on pragmatism, it is a very, very great honor to have Hugh Price here. A number of the speakers have mentioned that of late there's been a pragmatist turn in some corners, and I'm sure most of you know that Hugh Price was ahead of the curve on that and led the way for the rest of us. So, Hugh Price.
Thank you, Wayne, for that kind introduction. And thank you to everyone who's been involved in putting together this wonderful meeting. I don't get to many philosophy conferences these days, but I can't remember when I went to one which was so interesting. And it's especially interesting from my point of view because it's an opportunity to bring together two themes which have often been completely separate in my work. My interest in time and philosophy of physics and quantum mechanics and so on, and my interest in pragmatism. I mean, there have been occasions in the past where I met people who said, I used to think that there were two Hugh Prices. but here you're getting both of them.
There's more than two.
Okay, so sidestepping the Rhinoceros. Here's some novel perspectives from the 16th century. You probably all recognize the one on the right and realize why it's so novel. It's Copernicus's diagram of the heliocentric solar system. The one on the left is a novel for a different reason, namely that the poor creature depicted there was apparently the first rhinoceros to be seen in Europe for more than 1,000 years. So at least from a European perspective, it was extremely novel. These three images were actually produced by three people who were almost exact contemporaries of each other. So they were all born within 2 years of each other in the 1470s. Okay, but why have I got rhinoceroses on the same page with Copernicus? Well, that's because a few months ago, I came across a lovely image which seemed to me to represent a pre-Copernican rhinoceros. Here it is. I mean, it's obvious to us that there's something that rhinoceros hasn't yet figured out about its own perspective. And what it hasn't figured out is also a deeply pragmatic point. Here's James's famous quote, a central task of pragmatism is unmasking what James called the trail of the human serpent, or in this case, the trail of the rhino serpent. Okay, what I want to do in this talk is to show how this move, which I'm going to call in honor of the rhinoceros, de-rhinification, how that move, which is really another example of a sort of Copernican sidestep, how it can help us with quantum entanglement. So the rest of the talk is in 6 parts. First, a brief introduction to entanglement and non-locality. And I'm sure that lots of people here know this material much better than I do, but just a brief introduction for people who don't. What is entanglement? Well, Lenny Susskind here says it's the essential fact of quantum mechanics. He says one can know everything about a system and nothing about its individual parts. That's entanglement. And that's a very similar statement to one we find in Schrödinger in 1935 in the papers in which he coined the term entanglement. So Schrödinger says when two separated bodies that are each maximally known come to interact and then separate again, such an entanglement of knowledge often happens. He also said that it's not one, but rather the characteristic trait of quantum mechanics. Schrödinger was writing in response to what's now a very famous paper by Einstein, Podolsky and Rosen, the so-called EPR paper from 1935. And in that paper, EPR consider two-particle systems like the one on the left here, in which particles interact and then separate. And they note that measuring the nearby particle A can teach us a new fact about the remote particle B in virtue of the correlations required by quantum mechanics. Something not previously present in the quantum description. And different measurements on A can give us different new information about B. And they argue that these new facts must have existed already, although the quantum mechanical description didn't include them. The alternative would be that the nearby measurement was changing the remote particle in some way, And they thought that was absurd. As Schrödinger puts it, measurements on separated systems cannot affect one another directly. That would be magic. Well, a lot of people, not all that many people paid attention to this argument, but it was a very good argument. And one person who did pay attention to it a couple of decades later was John Bell. And John Bell famously discovered a major problem in the Einstein argument. He argued that the Einstein-Schrödinger view implies that measurement correlations satisfy what we now call a Bell inequality. Here's an example of one on the blackboard behind Bell here. But as Bell saw, quantum mechanics predicts violations of Bell inequalities in some cases. So if quantum mechanics is correct, Schrödinger's non-local magic must actually happen. This is how Bell himself puts it in the introduction to his first paper in 1964. He says, Einstein's idea is shown to be incompatible with the statistical predictions of quantum mechanics. It's the requirement of locality, or more precisely, that the result of a measurement on one system be unaffected by operations on a distant system, that creates the essential difficulty. Okay, but is quantum mechanics correct? Well, that was an open question for roughly another couple of decades. But we now have a verdict on it from a very prominent source. And paraphrasing a bit, the verdict is, yes, the quantum mechanical predictions are correct. The citation here for the Nobel Prize in Physics in 2 years ago, it says it was awarded for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Or as Aspect himself, Aspect is the one on the left here, as Aspect himself put it at the Nobel banquet, entanglement is confirmed in its strangest aspects. What are these strangest aspects? Well, I'm going to mention two. One is the apparent tension between non-locality and relativity. As Bell himself put it in a paper in 1984, we have an apparent incompatibility at the deepest level between the two fundamental pillars of contemporary theory. Here's Penrose 20 years ago. This is from Penrose's book, A Road to Reality. At one point he writes about the two mysteries of quantum entanglement. This is what he says the first one is. The first mystery is the phenomenon itself. How are we to come to terms with quantum entanglement and to make sense of it in terms of ideas that we can comprehend, so that we can manage to accept it as something that forms an important part of the workings of our actual universe? Some people put this question as, in terms of asking for a mechanism, in some very general sense, a mechanism for entanglement. Okay, well, my claim here is going to be that de-Rhinification can help us with both of those puzzles. We need some notions from causal modeling. And again, there are lots of people in the room who are more expert in this stuff than I am. I'm looking at you in particular, Jim. But here's the basic notions that we need. A collider, in causal modeling terms, is an event or a variable with more than one contributing cause. And this is depicted in causal diagrams, directed acyclic graphs, by converging arrows. And I guess that's why it's called a collider, because the two arrows collide. So the variable col at the top here is a collider because it's caused by both A and B, which are independent of each other, at least in terms of this diagram, because there's no direct arrows between them. Now, if we restrict our attention to, or condition on, as people say, the cases in which the collider variable takes a particular value, we'll often find a correlation between the causes A and B, even though they're actually independent. Well, it can work in the other direction. If they're not independent, sometimes this effect can hide a correlation. This can look like a causal correlation, but it's as people say, it's a causal artifact, the result of selection bias or collider bias. This is sometimes also called Bergson's bias or Bergson's paradox. Bergson was a Mayo Clinic physician and statistician in the 30s and 40s. And the paper which is standardly cited on this is a paper he published in 1948. But he was well behind the game. The basic point had been pointed out at least as early as 1911, when it was pointed out by the Cambridge economist A.C. Pagoo in a little piece in the Westminster Gazette. I think Pagoo chose the wrong venue to publish. Okay, so here's an example. I don't know if that happens in Canada, but as you all know, it happens on the other side of the border. Colleges select students, some colleges select students for academic ability and athletic ability, but don't require both. And let's suppose that those two kinds of ability are completely independent in the general population. And the Ivy College admission test looks like this. So the would-be students get asked two questions. Are you smart? Are you athletic? And they have to get a yes on at least one of those questions to get a yes on the question at top. Are you going to be admitted to Ivy? Now imagine that you're on campus at Ivy and you throw a ball to a random student, maybe one of these three. It hits them on the head and they fall over. They're not athletic, so they must be smart. You can go up to them and say, oh, congratulations, I understand you're very clever. I got this lovely example actually from a British statistician called George Davy Smith. I meant to give him a credit on the slides, but I forgot. So among Ivy students, then, there's a correlation between the two kinds of ability. If they don't have one, they must have the other. This might look like a causal correlation, but it's selection bias or collider bias. And one way of putting the fact that these correlations aren't causal is to point out that they don't support counterfactuals. So let's imagine a hypothetical Ivy student. Let's call her Holly. And suppose she's an athlete, but she struggles to get A's. Would she have been smarter if she'd been less athletic? Mm-hmm. No, if she'd been less athletic, she wouldn't have made the cut for admission to Ivy in the first place. Now we need a crucial new notion, which isn't, as far as I know, on the standard in the standard repertoire in causal modeling. It's what Ken Wharton and I, did I mention at the beginning that this is joint work with Ken? If not, I should have done. It's what Ken Wharton and I call a constrained collider. So here's an example. Suppose that Holly has a fairy godmother. Maybe it's this one, shared with Cinderella. And fairy godmother has decreed since Holly's birth that she shall be admitted to Ivy, one way or the other. So fairy godmother has constrained the collider variable, as we say, setting it to the positive value. Now, even fairy godmothers can't change the admission rules at Ivy College. So all she can do is to make sure that Holly qualifies one way or the other. So now it's true that if Holly had been less athletic, she would have been smarter. The fairy godmother would have taken care of it. And if Holly knows this fact, she could use it as a child in order to improve her grades. She just has to neglect her track practice. So constrained colliders do support counterfactuals. They look a lot more like a causal connection. Ken and I use the neutral terminology of connection across a constrained collider, because we want to sort of leave it open whether people want to think of this as genuine causation or not. Okay. Now we want to move to the quantum mechanics case. And first of all, look at some rather unusual cases of entanglement. And I'm going to call these W-shaped cases because they involve something that looks like a double W in a space-time diagram. So what's going on here is that there are two sources at S1 and S2, and they're each producing a pair of entangled particles. The inner particles from each pair go to a measurement at M, which has 4 possible results. If we post-select the cases in which this result is the same, say all the 0 cases, then the outer pair of particles behave as though they're entangled. This is called entanglement swapping. And this phenomenon, entanglement swapping, can be used to do Bell experiments, tests of the Bell inequalities. And some of the best recent experiments are like this. And this can be done, and we can find Bell correlations between the 2 outer sides of the W, between A and B. So what happens is we have 2 experimenters, typically called Alice and Bob. Each of them chooses a measurement setting, that's the little italic A and little italic B. And then they record the result of their experiment, the capital italic A and capital italic B. Okay, now those experiments can be done, and we can find Bell correlations. So does that mean, in Bell's words, that the outcome at B can be affected by the measurement choice at A? Well, not necessarily. As long as the result at M can be influenced by the choices at A and B, then it's a collider. And the Bell correlations we find between A and B can be collider bars. So as long as there's a causal path of the kind shown by the green arrows, we've got a collider at M, and any correlations we find between A and B can just be collider bars. Now, I didn't mention before that it's possible to do these experiments with the measurement in M in any temporal relationship to the measurements at A and B. And the case we're interested in is the case in the so-called delayed choice case, where the measurement M is happening in the future with respect to A and B. And this is a case in which it seems to be uncontroversial that we have a collider at M. I should say I want to give our chair a credit here, because the reason I first got interested in these cases, I think in 2012, was because there was very interesting discussion on Facebook about the significance of some delayed choice entanglement swapping experiments that have been done by somebody called Ma. And Wayne pointed out quite correctly that what had been discovered was in effect a selection artifact. I can't remember whether Wayne used that term, but he certainly put me onto the idea that in these delayed choice cases, the apparent entanglement could be regarded as a selection artifact. And several people have published about that, including Ken and me. Okay, so as long as we're in the delayed choice case and we've got a collider at M, Bell correlations can be collider bars. As we saw in Holly's case, collider artifacts don't support counterfactuals. If changes at A make a difference at M, there's no need at all for them to make a difference at B. Here's a toy model to help you think about that. If I actually had this collection of little plastic pieces here, I'm sure I could give them to you, and before I finish talking, you could have built a little W such that a small movement on the left-hand side of the W would transmit through and move the right-hand side. It'd be very easy to do. But now if you loosen the joint in the middle a little, you can make that effect go away, because wiggling the tip on the left will just alter the configuration of the joint in the middle and won't have any effect on the tip on the right. So the freedom of movement in the middle acts as a kind of safety valve so that changes on the left needn't produce changes on the right. And that's what's happening in these delayed choice entanglement swapping Bell experiments. So we have a safety valve, and I represent that by the open green padlock. So in this special kind of Bell experiment, Bell correlations between A and B needn't imply non-locality or Schrödinger's magic. Okay, but now what we want to do is to consider what happens if we constrain the collider at M. That is, if there's something like Holly's fairy godmother, which ensures that the collider variable takes a particular value. So if there was something in physics that could act like Holly's fairy godmother, constraining the collider at m, locking the measurement outcome to a single value, well, then the safety valve would be closed. Changes to the measurement at A could no longer affect the result at the collider at M, so they would have to affect the result at B. So in effect, we get back genuine Bell non-locality. Okay, but where are we going to find something to do that magical job in physics? Well, luckily there's magic even in physics. And the bit of magic we need is something called the Horowitz-Maldaceno hypothesis. And this is a proposal for solving the so-called black hole information paradox. Since the work of Hawking in the 70s, there's been a debate as to whether, as Hawking initially thought, his results showed that information could never escape from a black hole, in apparent tension with the sort of unitarity of general relativity. Well, that became a hot topic for debate, and not only for debate, but also for bets. I think Hawking had one with, I forget who the other people were. And Hawking eventually conceded that he'd lost the bet, and that there were ways in which information could get out of black holes. And one proposal for how that could happen is this one from Horowitz and Maldaceno. The diagram here comes from a paper about it by Lloyd and Preskel in 2014, but the description underneath comes from Horowitz and Maldaceno themselves. They say, in the process of black hole evaporation, particles are created in correlated pairs, with one falling into the hole and the other radiated to infinity. So that's what we have here. This is the sort of basis of Hawking radiation. There's a random production of pairs on the horizon of the black hole. And one particle falls into the black hole. And the Horowitz-Maldaceno idea is that at the final singularity, it meets up with infalling matter, infalling information. So the correlations, that's the correlations in those pairs of particles produced on the horizon. The correlations remain even when the particles are widely separated. The final state boundary condition at the black hole singularity acts like a measurement that collapses the state into the one associated with the infalling matter. This transfers the information to the outgoing Hawking radiation in a process similar to quantum teleportation. Now, in this particular passage, they don't say explicitly that it has to be a measurement which can only take one value, but that's crucial to the proposal, because otherwise it's not going to support counterfactuals. And clearly they need counterfactuals, because they need it to be the case that if different information had fallen in, different information would have come out. This is from a paper by the Cambridge physicist Malcolm Perry, writing about this idea a couple of years ago. The diagram from Perry's paper that I've stolen here, he calls it the Penrose diagram of a black hole that evaporates completely, together with a river showing the expected flow of quantum information. The river is the sort of zigzag-shaped strip there. Perry says, the interior of a black hole is therefore a strange place where one's classical notions of causality are violated. This does not matter as long as outside the black hole, such pathologies do not bother us. Well, my claim is that such pathologies have been bothering us for almost a century, because entanglement is much the same thing, although it relies on something more common than black holes or fairy godmothers. So where are we? We've seen how, in a very special kind of case, a W-shaped Bell experiment with the central measurement inside a Horowitz-Maldaceno black hole, Bell non-locality can be a combination of two things: regular old collider bias and a constraint on the collider, locking it to one value. The last step is to show that the same explanation works in much more ordinary cases, and this is where we need the de-Rhinification. Okay, let's look at some ordinary cases. We call these V-shaped Bell experiments for the obvious reason. We just have one source producing a pair of particles, which goes to Alice and Bob. There are various states. In the version we're looking at here, there are 4 possible ways we can prepare the pair of particles initially. So that the two entangled particles go to measurements at A and B, where the experimenters choose a setting and record an outcome. And as long as we keep the initial state C constant, we'll find Bell correlations in the results. But those Bell correlations disappear if the initial state is allowed to vary at random. But we can recover them by pre-selecting, that is, by throwing away all the cases except those in which the initial state has one particular value, which looks similar to what we were doing in the W-shaped case. In other words, we can start with a version of the experiment in which the initial state is chosen at random, say by a coin toss. We get no Bell correlations in the experiment as a whole, but we can find them again if we pre-select on just one of the initial values, discard the other cases. Does this mean that we can regard the Bell correlations as mere selection artifacts, just as in the W case? Well, no, or at least not yet, because there's still a very important difference between the two cases. In the W case, the result at M is a collider influenced by the measurement settings on both sides. That's why it can act as a safety valve, absorbing the effects of changes to the settings, so that there's no need for Bell non-locality between A and B. To get the same thing working in the V case, we need a causal structure like this. That is, a causal structure in which the settings choices by Alice and Bob make a difference to the initial state that we had at the beginning at C. But that seems crazy in the real world. Quantum measurement choices in the future don't influence ordinary coin tosses, right? Right. And without that, we don't have a collider at C, and so we can't use our story about Bell correlations being collider artifacts. What are we going to do? Remember the rhino's snout. Here are some ordinary time asymmetries that we take for granted in ordinary life, much of the time, and in physics and philosophy. The future is open, but the past is fixed. In ordinary means-end reasoning, our ends are typically later in time than our means for achieving those ends. We typically control the initial conditions of experiments and only indirectly their final conditions. And causation runs from past to future and not vice versa. I'm going to brush aside here many subtle issues about such asymmetries, but let's lump them together under one heading. I'll call them initial control. I'm very fortunate in that I know that Carlo is going to be talking about at least some of these asymmetries this afternoon. So I can afford to sweep them under the carpet at this point. Where does that initial control come from? Why is our universe asymmetric in that way? Well, again, there's a lot of room for disagreement about the details, but there's a lot of agreement about the big picture. This is Penrose's version of the big picture. So I don't know if you can read the caption there. I'll read it out in case you can't. The caption says, in order to produce a universe resembling the one in which we live, the creator would have to aim for an absurdly tiny volume of the phase space of possible universes, about 1 in 10 to the 10 to the 123 of the entire volume for the situation under consideration. The pin and the spot aimed for are not drawn to scale, Penrose tells us helpfully. So, as I said, this is Penrose's version of the big picture. Penrose's depiction of the fact that our universe seems to have begun in an extremely special low entropy state. These days often called the past hypothesis, a terminology introduced by David Albert following, I think, Feynman. Okay, I want to focus on the entire collection of universes from which Penrose's creator is making their choice. So everything in this floppy white box. By definition, this collection doesn't have the time asymmetries that result in our actual world from the special initial choice. Let's call this the unpinned regime. Let's think about causation in the unpinned regime. Can we talk about causation at all? Well, yes, apparently, as long as we restrict ourselves to what some physicists think is the only respectable notion in any case. Here's a quote from Hawking again in 1994. Hawking says, and this is after he's made some dismissive remarks about Reichenbach's work on the direction of time. Hawking says, in physics, we believe that there are laws that determine the evolution of the universe uniquely. So if state A evolved into state B, one could say that A caused B, but one could equally well look at it in the other direction of time and say that B caused A. So causality does not define a direction of time. Well, that particular notion of causality doesn't, but I think many of us feel that there are other interesting notions of causality that do, but we don't need to get involved in an argument with Hawking on that point. What's important is that there's some thin time-symmetric notion of causation which we can continue to use in the unpinned regime. And with that notion of causation in mind, let's go back to the V-shaped Bell experiment. Now imagine that the experiment we're looking at is depicting an experiment which is just happening at random, somewhere in the vast space of possibilities that is the unpinned regime. And if you're worried about the idea of quantum experiments happening at random, then I've got bad news for you, because there are much more serious things that we have to worry about once we get to that regime, including what are now called Boltzmann brains. So the idea that we might think or I might think that I'm a member of a community on a planet which has a history and so on, but I could be mistaken, just because my brain is just a little fluctuation somewhere in this vast kind of time-symmetric regime. Okay, but that's the kind of thinking we need here. We need to think of the experiment depicted on the right here as happening in this regime. Do we have any reason to deny that we have the effect shown in red in Hawking's weak time asymmetric sense of causation? Well, no, because we've explicitly turned off initial control in describing the case. So now the safety valve is open and everything works just as in the W case. Bell correlations can be explained as collider artifacts. And if that seems implausible to you, then I think you're still stuck in the pinned regime. Here's a toy model to make it easier to think about what's happening in this case. So imagine that we have triangular poker chips, each with 3 spots labeled A, B, and C. And suppose that they're subject to the rule that the 3 spots can't all be the same. So they can either be shaded or unshaded, but it has to be at least 2 of one and 1 of the other. I mean, at least 1 of one and 2 of the other. Never all the same. Imagine that you're selecting chips like this at random from a huge urn. And suppose that C is specified to be fixed. You might do this by making sure that the urn was filled with chips for which C was always shaded, or you might just throw away the unshaded one as they emerge. So if C is specified to be fixed, then a change to B requires a change to A in the configuration shown, because otherwise we'd have 3 shaded spots. And unlocking C removes that effect, because a change to B can now be absorbed as a change to C. So here in this very simple example, we have an illustration of the kind of collider structure that we need to imagine in the unpinned regime for those V-shaped Bell experiments. I mean, I fixed C because I was trying to get you vaguely thinking to fixing something in the past. But you can fix A or B. Obviously, this example is 3-way symmetric. So it's an example of how detached the notion of collider that we need is from spatiotemporal considerations. So that's in effect what's happening in a V-shaped Bell experiment in the unpinned regime. Okay, but that was a highly unrealistic domain that we were talking about. in the real world, we are stuck behind the Rhino snap. So we're all downstream from Penrose's creator's absurdly sharp pin. So in the real world, the collider at sea is, ask me in Q&A about why I say almost always. I don't have a slide about this, but there's an interesting discussion to be had. But at least almost always the collider at sea is constrained simply by our ordinary ability to set the initial conditions of an experiment. And that closes the safety valve so that changes at A have to show up at B and vice versa. And that's Bell non-locality. But the detour via the unpinned regime shows us that in this case, just like in the constrained W case, non-locality can be the result of two things: collider bias and a constraint on the collider locking it to one value. Okay, so this is the sort of the structure of the cases we've looked at. So these are the two ordinary cases. So in the ordinary W case, we have a collider here. These things are naturally thought of as outputs. That's in effect why they're unconstrained. Whereas in the normal V-shaped case, these things are inputs. That's why it's natural to think of them as constrained. But to see the sort of commonality here, what we had to do was to bring into view the two missing cases, the exceptional cases. And for the W case, we did that using the Horowitz-Maldacena proposal, thinking of this measurement as taking place in a black hole. And in effect, what that does is to convert the output here into something like an input that's imposed by the Horowitz-Maldacena condition in the black hole. And then in the V-shaped case, that's the normal case. To bring this case into view, we had to move into the unpinned regime. And in effect, moving into the unpinned regime, we could think of it as turning C into a kind of output, because it's no longer something controlled. So it's not an input in the normal sense. In fact, in a sense, moving to the unpinned regime is just throwing away inputs altogether. Okay, so how does this help with the strangest aspects of entanglement that we mentioned at the beginning? Well, here's Penrose again on the first mystery. How are we to come to terms with quantum entanglement and to make sense of it in terms of ideas that we can comprehend? Well, colliders and collider bias are familiar. They're not mysterious at all. And although constrained colliders are not familiar and not previously named as far as we know, they're both easy to understand and staggeringly ubiquitous once we understand the significance of Penrose's own point about the creator's pin. What about the tension between non-locality and relativity? Well, here I think it's less straightforward, but what this explanation proposes to do is to explain Bell correlations as a combination of two things: dependency relations within light cones and boundary conditions of various kinds. And neither of those ingredients individually seems to be in tension with relativity. And it's long been noted that zigzag processes might, in principle, provide a relativity-friendly key to the issues identified by EPR in 1935. This is the French physicist Olivier Costa de Beauregard, who was a student at De Broglie in the late 40s in Paris, and came up with the idea that there was a loophole in the EPR argument, because what was happening on one side might affect what was happening on the other side, not directly in a way which would be in tension with ideas of action, prohibiting action at a distance and space-like action. But it could do so indirectly via a process which went via the past world lines of the particles involved. So this notion of a sort of zigzag explanation applicable in EPR and in Bell cases has been on the table since, well, Costa de Beauregard first published on this in 1953, and then after Bell published his results, proposed that it was the solution needed to avoid non-locality. And what constrained colliders seem to do is to give us a kind of mechanism, at least an operational mechanism, for how we get such Parisian zigzags. Okay, so the key steps in the argument. Noticing something special about our viewpoint, and thinking about things sideways without that special restriction. So that's it. Thank you.
And this is also a novelty. For the first time in history, a philosopher with an hour of time has finished in 40 minutes. I'm not surprised that Carlo has comments. Go ahead.
Thank you very much. This is I find this very fascinating. I've been, of course, like everybody in my trade, struggling with entanglement, and I've been trying to follow your ideas for a long time, and I do think this is extremely interesting. I would like to see what you react by reading what you say, a strong part and a proposal part. The proposal part is the specific, I wouldn't say mechanism, but sort of how to think about what happened in EPR. But the thing to me, there's a stronger message, which I think is new and completely new, and it seems it should be uncontroversial, which is the following. There's a mystery, which is EPR. How would this spell? Okay. There's another mystery in physics, which is the direction of time, the past and the future. Okay. One can turn it around a number of ways. We keep discussing about that. Why entropy was low? Why the initial continuum? And I think something you're showing completely clear that the first is the case of the second.
Yeah.
The two are strictly related.
Yes.
And you can any way of coming up a story about the first requires it's actually a story about the second. That is I haven't found this before in the idea. So that I think it's a bingo. That's it. It has to be true. And one way of putting it is that one thing that people say is that the Bell initial qualities appear to violate Reichenbach common cause postulate or whatever. But Reichenbach common cause, Reichenbach in his book presented as a theorem, not as a postulate, that follows from the what you call the gradient of entropy. So that's a problem. It's a problem about past and future. It's not a problem about non-locality. Is that do I get this main message?
Yeah, I don't know if I quite understood the bit at the end about Reichenbach, but certainly the main message, I think, as you correctly see, I would put it by saying that people just hadn't noticed what a powerful resource the low entropy past is, so that it can do this simple job, and once we see that it can do it in the future, in the W cases, then it's easy to transfer it to the V-shaped cases, where the resource has just been on the table for decades as part of the standard explanation of all the ordinary time asymmetries.
Thank you.
Patrick is next.
Hi, thanks for a really interesting talk. I'm curious about, so if I've understood the proposal correctly, it sounds like in the entanglement case, when we have the upside down V, part of the intuition is that the way in which we're constraining the relevant collider is by intervening on it, in the sense of fixing the value that the preparation is going to take on. But so my question is, if you look at the other colliders and you think of constraining them, the nature of that constraint can't just be one of intervening on the collider variable, because if you sort of ignore all the other causal influences on that variable, you're going to sever the relevant collider bias connection. So I guess I'm wondering.
Sorry, Patrick, are we talking about V-shaped cases or W-shaped cases here?
So in the upside down V-shaped case, sorry, the case that you started off with on like the first slide, where you've got two, you've got
Okay.
athletics and academics.
Let's go back.
Sorry.
W-shaped case.
Yeah.
So are you talking about this case?
Yeah. So yes. So if you intervene on M by
well, we're not considering that possibility. So what in this case, the only intervention variables we're considering are little a and little b, the ordinary setting choices.
Mm-hmm. So in this case, it seems clear that the way that the constraint on the collider is implemented is not by intervening on M.
Exactly. I mean, that's another way of saying that we're thinking of we're thinking of M as an output.
But in the case where M is at the bottom.
Yeah, and is come to be called C, which may be
yes. In that case.
Yeah, so here, yeah, I mean, you are in effect in the ordinary case thinking of C as an intervention variable,
okay,
taking 4 possible values, and as I put it near the end, that's to think of C as an input. So, and that's a very helpful way of representing the difference, and really it's the only difference between these two experiments, because otherwise the correlations can be exactly the same. Okay, but then the move I made was in the W case to, in effect, turn M into an input by having a boundary condition on it that constrains it. At least it's no longer an exogenous variable. And in this case, in effect, turn C into an output by working in the unpinned regime where there are no inputs anyway.
Right. Okay, cool, thanks.
Pascal is next.
Yeah, thank you for the great talk. It's really fascinating. I have a question that has like 2 sides. The first one is if any other correlation could be in principle be explained by positing some constraint colliders, and if you have a methodology to distinguish between which ones should be taken like as causal correlations directly and which ones shouldn't, and how that relates. So yesterday we saw a talk by Alisa Bogulice, where she said like that part of pragmatism is like the idea of fallibilism and finding the dynamic conception of truths, and that works towards error corrections. Is this compatible with that kind of methodological pragmatism? Because it seems to me like it relies in some way in an explanation or an account of best correlations that will not satisfy those pragmatic conditions, if I understand correctly.
Yeah, it's a very interesting question, and if I could just sort of reorient it a little bit. Penrose's second mystery of entanglement is, why do we only find this thing in such a sort of hidden place? Whatever the explanation for entanglement is, why don't we see much more of it? And what we've offered here provides no sort of answer to that question at all. And of course, it's if this is the right story about entanglement, it makes that second question even more pressing. And the way I see it is related to the original formulation of your question is, can we think of other cases of correlations or counterfactual supporting correlations elsewhere in science or in everyday life, which can also be explained in this way? If there are such examples, then it suggests that it's not confined to quantum mechanics at all. And that would be a surprising result, I think.
Chris, next.
So I'm not sure what your view is of the Hawking proposal that we would have a time symmetric notion of causation. So is that your preferred analysis of causation, or is that...
Oh no, absolutely not.
Yeah, okay.
I'm an interventionist, and a
Yeah.
pragmatist interventionist who thinks the direction of the interventionist notion of causation comes from our orientation as
Okay.
agents. Yeah.
Yeah. So then in the I mean, this is related to Carlo's question. So one of the main themes is really once you take on a time asymmetric notion of causation, then you have the resources that you're characterizing as the unpinned regime, or sorry, the pinned regime. Once you have a low entropy past hypothesis, that's what gives you the resources to...
Yes, and
Yeah.
there. I think this is what Carlo is going to be talking about this afternoon. There are some options about how we get from the pin to this asymmetric notion of causation. I mean, at least roughly speaking, there are two main paths. One of which is to try and reduce the asymmetry in causation to the thermodynamic gradient in some way. The other is to put the emphasis on the perspective of agents.
Right.
But of course, the existence of us as agents is going to depend on the pin.
Yeah.
Yeah.
Okay, great.
Jack, next.
I just wanted so my question is quite similar to Pascal's, so this seems like it's trying to present a new kind of methodology to approaching physics questions in terms of constraining initial states and kind of leaving your underlying dynamical assumptions the same. So I wanted to ask if you think there's a reason why this approach has not been adopted very much at all previously, and why dynamical approaches were the default way of addressing these things, when in principle you could have taken this kind of initial state constraint approach with regard to many past questions within physics, and it was not done so.
Well, I think that the approach is already on the table. It's a sort of orthodox view that the explanation of the various asymmetries we see around us come from a combination of two things: a time symmetric measure on a space of possibilities, and the past hypothesis. So that's basically the same move. It's a move that starts with what I'm calling the unpinned regime, and then thinks about the effects of applying a boundary condition to it. So as a resource, that kind of move in physics is already a familiar one. It's just that, as I said in answer to Carlo, I don't think anyone's thought of applying it to the case of quantum entanglement.
Well, just to add to that, right? So obviously the statistical mechanics case came to mind immediately for me as well. But I was wondering if one looks beyond those to things like past gravitational theories, and why it would not have been considered a viable move to keep the basic philosophical presumptions of Newtonian gravity, but adjust global constraints in such a way as to capture the empirical side that you want to capture?
Yeah, it's an interesting question. I mean, in the kind of literature in the foundations of quantum theory that I'm kind of come from, where people are interested in retrocausality, I mean, that's becoming very much more muted in this idea, because we only need retrocausality in a regime in which we don't have any direction to causality anyway. But in that, although it's an interesting question whether you might still need it once you get below the operational level. But in that domain, there are plenty of people thinking in terms of setting things up in terms of global constraints rather than a dynamic picture. And my little example of the triangular poker chips is naturally thought in terms of a global constraint, because there's a global constraint on the chips that they can't all have all the spots the same color.
Ollie.
Thank you. That was really awesome, and it is fun to see the time start to come together with this. Just a small point, and then a question to clarify the kind of structure of your argument also, but I think it's related to Chris's question. There is in fact a kid's book called Harriet Hamsterbone, which does exactly like this thing. She has a fairy godmother that is very evil and declares that she's going to die at age 12. And Harriet takes this as a chance to engage in lots of very dangerous activities because she knows that she will not die before age 12. There's a whole series of them anyway, so that might be.
Oh, wonderful! Thank you.
So I think it was fun. We could call it Harriet instead of Holly.
Yeah, no, that's much better. I mean, obviously, I had Christmas themes in my mind. But
Well, and I just wanted to ask about the role that the unpinned regimes are playing here. Like, if I have other reasons perhaps for not wanting to say that those other possible universals are genuinely possible, are you using the sort of going via the unpinned regime to sort of illustrate what we could do without having to go through there? Or is it sort of required that we think of those as all genuinely possible such that we can then make the comparison?
okay, that's an interesting question. I don't think I'm doing anything more than is involved in the statistical mechanical case that I mentioned just now. This orthodox story about the origin of the thermodynamic gradient. We start with a regime with a time symmetric measure in which there's no such asymmetry, and then we consider the effect of imposing a special boundary condition on it, usually in the past or sometimes at both ends. Now, would your question map over in some way to that case? I mean, to some worry about the status of the time symmetric measure?
No, that does in fact alleviate my concern, because then it looks like using the unpinned regime is a very good illustration for how you could think of going around the rhino horn, but it's not, as it were, required.
Yes.
That you impute.
Yeah. No. So I mean, there's an interesting issue here about to what extent the Copernican shift needs to be something which is physically possible. And I think if you look at the sort of historical cases, you'll probably find a kind of gradation. I mean, obviously, at Copernicus' own time, it wasn't physically possible, but it became physically possible. I don't think this case will go that way, but I don't think I'm using a step which isn't already on the table.
Okay. Ask me
Just
quick.
a very quick comment, and it's got nothing to do with your argument. It's got everything to do with rhinos. Can you show the first rhino?
Yes.
The doer one.
Yeah.
I showed this to my daughter, who's a vet at the Toronto Zoo, and she specializes in big animals, including rhinos. And I said, look at how ludicrous Europeans thought rhinos looked. She said, don't be absurd. That's a caricature of an African rhino, but an Asian rhino looks a hell of a lot like that.
Oh,
So that's a plausible sketch of an Asian rhino. I don't know what Dewar was looking at.
well, he wasn't looking at a rhino. He never saw the rhino. So he had some sort of description or sketch by somebody else. Yeah, I don't know off the top of my head whether it was an African or an Asian rhino that was brought to Europe in 1550.
Thank you for that historical comment. All right, let's take our finger once again.